Most of us, we start with this kind of shameless advertisement at the end of the conference or at the end of the presentation, and I'm just going to do it right at the beginning and invite all of you to come to Dioxin in Vancouver this year. They're going to have a very, very interesting program. We have more than 400 abstracts received so far, and we are hoping to receive another 200 or 300. So it's going to be lots of new information, the latest and greatest about Dioxin. And Vancouver is probably one of the most beautiful cities in Canada, and you'll enjoy the city and the ambience of the city. It was a few weeks ago that I received an email from Heinz and inviting me to this conference. And I said to myself, Heinz might not have a very good memory. Last time, when I attended this workshop, it was in Niagara-on-the-Lake. And I have the distinction of giving my longest lecture ever, and if anybody can surpass that one, let me know. I started my talk about 9:15, and I finished my talk about 4 p.m. That was a very long talk, right? No, it was a little accident in between. So it was a storm that came, and right at my fourth or fifth slide, all of a sudden the whole hotel went dark. We didn't know what was happening, and the power got back till about 3:30. But in between, we had a great time. We had very good networking, probably the best networking, combined with a little bit of wine tasting, and enjoyed the ambience of Niagara-on-the-Lake. For those of you who haven't been to Niagara-on-the-Lake, I would strongly encourage you to do it. And if you enjoy wine, and particularly ice wine, is the best place to go. So, with that, let's talk about phthalates. I'll be talking about 35 phthalates, but this is a misnomenclature as far as I'm concerned, because these are 35 phthalates that have one basically CAS number. And in reality, there are many more. So we'll go talk about it. And before I go there, I would like to acknowledge basically this work has been done by Tommy, who's my chemist, and Gwezina, who's the senior technologist in my lab. And they're all working very hard to make me look good. And that's a very tough job. So, I always like about the mistakes. You know, we have had so many mistakes. But in my world, mistake doesn't exist. Mistakes are learning opportunities. Some of us learn from our mistakes, and this was another one, that PVC was accidentally made. Basically, they put some vinyl chloride right in front of sunlight, and it polymerized. But some people will say, oh yeah, this went back, throw it in the garbage, and that's it, move on to the next, and forget it. And some other people take a look at it and see what's in it. And they came up with a polymer that has been used. But if you look at the consistency of PVC, I don't know if you have ever touched PVC alone, to me it has a consistency like sugar. And to make something useful out of it, what do you make with sugar? You make brittle. And brittle is very sort of, you can't ply it, you can't do anything with it. So what you do is you turn sugar into caramel, right? You add a little bit of butter to it. And then it becomes nice, soft, pliable, and you can pour it on your ice cream, or you can have a nice piece of caramel and enjoy it. To me, phthalates is like butter that you add to your sugar. These are the compounds that you add to a very rigid material to make them pliable, and as a result, it has turned into one of the things that has been widely used in many areas. But as you know, these materials are not reactive, they're only additive. And they can easily leach out. Many of you, summertime is here, you go out, buy nice furniture, backyard garden furniture. Nice, shiny, very comfortable. By the end of the summer, when you want to take it back inside, they're brittle and they're cracking because the phthalates have been leached out of them. So basically, 90% of the phthalates are being used for PVC, and the other application of it that are being used, the lower molecular weight phthalates, are used as a carrier in personal care products. So we can see that, these plasticizers are everywhere, and as a result, it can cause havoc with analysis. So basically, why we need to use to study them? They have some endocrine disrupting properties. They have been found everywhere, including in household dust, and basically they have some toxicity, endocrine disrupting properties. How these things are made? And why I'm talking about synthetic chemistry today. Are we a synthetic group? No. But we don't know where we come from. Then we can go back. So basically, in the industry, we take benzoic anhydride, and we react it with alcohol, and then we react it with another alcohol. And that's how we form phthalates. This is an exothermic reaction that happens very quickly. This one requires energy. So as you can see later on, this is not very stable, and it likes to come back to this state. So what are the phthalates we are looking for at? This is the list of the phthalates, and obviously, by the time you're filling your questionnaire, there's a question on phthalates at the end if you haven't seen it right now. So you have to answer the phthalate question before you get your $5 Starbucks. But as you can see, these things, they all have a single Cas number, but they are a single compound. You can see, for example, these are the ones that I call the single compound. They're one compound. The two alcohols used for esterifications are the same. Then you get the iso, which is basically a mixture of alcohols. And you get diisoheptyl, diisonanyl, diisodecyl, diisondecyl. And you can see in each one of these, they're using a lot of branch material. And another one that's very interesting, it's commonly referred to as J-flex, has so many isomers that, we don't have a clue. We cannot resolve them on a GC column. So I'm talking about 35. I will be talking about 3,500, maybe 35,000, who knows. So that's a challenge. Where's the analytical challenge? You remember the synthetic path. If you start from the synthetic path, we can go backwards. So when you put your phthalates in an electron ionization system, it goes and forms the monoester and benzoic anhydride. So that's the mass 149 that many of you have seen in your GC column playing havoc with you, and out of the phthalates are coming from. So if you design an experiment to look at all of these phthalates and look at mass to charge 149, can you identify individual congeners? They're all going to be all over each other. And that's the typical spectrum you get. But then, as you can see, these compounds are ubiquitous in the environment. We cannot find any high purity solvent that does not have any phthalates in them. And the other interesting thing is that we open up a bottle of solvent in the morning, we inject it, inject a sample of it into the GC or LC, and by the evening, if the peak is about this big, by the evening is this big. So you can see that it's constantly been absorbing phthalates from the surrounding environment. And this is basically asking everybody just to open the cap, pour some in, close the cap immediately. So the environment is also adding to the analysis. So we basically use high purity solvents, but still we have some background there. All of the glassware is baked at 400. We use closed systems. Like we cannot use the classical column that is dripping, silica gel dripping. And also we have to basically use the laboratory bank. And to date, I have not been able to find a single water sample that does not have phthalates in them. So what we do for our blanks, we basically take the reagent and we subtract it from our actual samples, numbers. So why we went with LCMS? This is a GC-able compound. And as you can see, somebody like me who has been growing up in the GC world always says, whatever you can do with GC, you shouldn't do it with LC. Right? Dave likes that. But you can see that most of these compounds, most of the ISO compounds, instead of producing lots of peaks, they produce only one peak. And the other thing is that under ESI conditions, we are getting M plus or M plus H plus. So now we have a characteristics of each molecule that we can resolve. Even though when you go MSMS on it, everything will produce a master charge. The product ion will be master charge 149. The precursor ion represents the molecular weight of the compounds of interest. As a result, we can be able to separate them. And for this one, we use the phenylhexyl column. Very simple, sub 2 micron. And another thing we did, in this case, we put a scrubber column right before the injection port. Our mobile phase is not immune from phthalates. And in order to reduce our blank, all the mobile phase is going right through a scrubber column before the injection port. As a result, the background drops quite heavily. And for that, we use the C18, 2.5 micron, and 2.1 biofon. So with this, we were able to collect all of the phthalates in our mobile phase. And if you use the shorter column, which initially we did, we get 2 peaks for every compound. One, the system peak, one standard. With this one, the column was long enough that it held on to all of the phthalates in the mobile phase, and it was eluted right at the end of the run. So we only get 1 peak per compound. And obviously, we operated the triple quad in MRM, and we basically look at M plus 1, the protonated compound, going down to master charge 149. So this is a simple, typical LCMS conditions, nothing out of ordinary. And this is what we get. Now you can see, instead of getting a big zoo that you get in the GC system, you're getting something that's manageable, and also they are resolvable based on the parent or the precursor master charge ratio. And all of them is well resolved. So, how to extract this? Obviously, everybody around here knows about QuEChERS method, and this is what we did. We used 10 milliliters of sample, and we added to a glass centrifuge. We put our deuterated phthalate mixture, add acetonitrile, shake it, and then take the acetonitrile, evaporate it, and inject it directly into the LC system. As I said to you, this is what we get. An HPLC grade water is the cleanest we had so far. But as you can see, these are the phthalates that we see in the background. We look at the recoveries for this method. You can see for such a large group of compounds, we get a recovery between mainly 80 to 120, with just 1 or 2 of them that not being very well, it's a little bit on the lower side. But again, for a very vast group of compounds, it's very hard to optimize. You optimize for one end, you lose on the other side. So that's the best we could find. And then we looked at the recoveries on the internal standards, and we can see that as we go from blank water, which is basically the HPLC water, to the industrial effluent, to the influent and effluent, we can see that the recoveries keep going lower and lower and lower. But one interesting thing is that the influent had better recoveries than the effluent here. And I think this is something that probably it's affecting with the performance standard that we have put in our system. So for solids and biosolids, how we did it? We used the same thing. We basically used the QuEChERS system. And in this case, we used 0.1 gram of biosolids, and we put it in a centrifuge tube. We spiked it. We put HPLC water on it. And then we went through standard QuEChERS. And in this case, we used the disperse solid phase extraction to remove all of the interferences. And then basically we took the extract, and this is the disperse solid phase extraction conditions. And then the inferences adhering to PSA for 30 seconds. And then we took an extract and took it for analysis. And again, this is the kind of recoveries we get. Oops. We get from Ottawa sand, again, not bad, somewhere between 100 and 150%. But again, you can see the blank interferences are there. You can't get away from blank interferences in this work. And then you get a sample. We go with Lake Erie. Again, you can see the recoveries are starting to get a little bit lower, not in a better condition. And then when you go to basically from biosolids, this is the kind of recoveries you're going to get. And you can get here some of these in the order of 20, 30%, and some of these are not the best situation. But that's the best you can do when you're dealing with so many different compounds at the same time. How this works in a wastewater treatment plant, we just went in, we used basically automatic sampler. It worked over a 24-hour composite every 30 minutes. It's a Sigma 900 refrigerator sampler. And after that, once we took these, what we call the pop bottles, the 20-liter pop bottles, we fill it up, we shake it, and then we subsample 1 liter amber glass, Teflon line. And then we keep them cool, and we bring the samples back to the lab, and we immediately extract them. Because again, there's a chance that phthalates might go to phthalate monoesters in the wastewater treatment plant. And this is what we get in the concentration of phthalates in various wastewater treatment plants. The interesting thing you can see here, the most important part here is the blank contribution, not very much, even though we have blank. And the other take-home message is that you can see that the influent is much higher than the effluent. If you take these and we calculate for the removal efficiencies of wastewater treatment plants, with the exception of a few, and some of them are primary and lagoons that are in the 70%, the vast majority of them are 90% plus removing phthalates. And the phthalates is moving to biosolids. What about the concentration of the biosolids? Again, you can see here, these are the concentration of the biosolids in various wastewater treatment plants. And obviously, it's time to do a little bit of mass balance. But I'm waiting to get all of the flows from different plants to make sure that we can do the mass balance and show what's the percentage that's going to the biosolids. But a rough calculation shows that most of it ends up in biosolid. And in addition, what we did, we looked at the monoesters in the wastewater treatment plants, influent and effluent, and the contribution is not high. We can measure them, but it's in the order of 100 to 1,000 times less than the parent compounds. So, in summary, we have been able to develop an LCMS method that's very quick, very efficient for measuring the phthalates. One of the effective components of it was to add the scrubber column, which removes the phthalates from the system. But again, another thing you have to realize, in this case, less is more. The less sample you use, the less background you have, the less interferences and the less signal suppression you get. So if you're coming from the GC world that you always can take more sample and analyze more, going to LC doesn't work that way. We used sealed system, and we were able to get relatively good blanks, but again, I don't know if anybody can do any kind of phthalate analysis without any blank contributions. Additional cleanup we did with dispersive solid extraction, which showed to be very good. And recently we have started having an ultra clean lab, which we are hoping to be able to use it. One of the concerns right now is that if you look at the Canadian Environmental Protection Act, it requires that if a compound is toxic at a certain level, at the PNAC, predicted environmental no effect concentration, you have to be able to measure it at that level. And when you do the PNAC measurements for some of these phthalates, the values that you want to come is about 10 times less than what you see in your blank. So again, we are hoping that by moving to the clean lab, we should be able to reduce the blank contribution and be able to get lower with the blank samples. We had our method. It's validated. We look at 350 wastewater samples from various municipalities. We showed that in vast majority of the cases, with the exception of one or two, that it was the 90% plus, and the other ones were 70% plus removal efficiencies. And the levels of phthalate monoesters that we found in our wastewater treatment plant Influent and Effluents were very low, so I don't think that the conversion to monoesters at this point is of significance. And likelihood that the adhesion to the biosolids is the main route of removal of phthalates from wastewater. I would like to thank Charlene Smith and her team that they collected the samples from municipal wastewater treatment plant. Wastewater treatment plant operators, it's always nice to be able to go and collect samples, and they're always welcoming letting us to go in and do our work and taking away time from their work, and also funding from this study that was provided by Chemicals Management Plant. And with that, I thank you, and if there's any question.
We've been seeing sort of a turn to alternates to the phthalates, like cyclohexane and tricarboxylic terephtalates, things like that. Have you looked at any of those? Are they part of the program?
They are part of the program, but they're not part of the immediate list of assessments, and we will be looking at them in the future.
Looking forward kind of thing.
Yeah.
We did some work with Shirley-Ann 2 years ago to measure estrogenic activity of the wastewater, and we were having issues with the blank and the sampler itself. So, and we thought that maybe it was phthalate leaching from the tubes that were used. Did you use any specific material to collect?
No, we use the same ones, but the phthalates that has been coming in the system, I don't think they were any higher than the blanks that we were getting. So I assume that the phthalates are coming from from the water that they've been using for their blanks.
Okay, so you didn't do a blank. I was curious because we had no way to measure the phthalate. We just assumed that was the source, and it seems you might have used the same samplers.
We used the same sampler, but basically it was done. But basically, we took we use molecular water to do the blank study on it, and we took a molecular water that was without running it through the system, and there was no difference between the two.
Okay.
So, again, with the precision of the method, I don't think we can say anything, that it's coming from water or it's coming from the sampler itself.
Okay, but you didn't see a high increase after
No, it
using
was
the
not
sampler?
a very high increase, no.
Thank you.
Just curious about if you could briefly discuss, or just mention the approach that you use to determine an MDL with background contamination, with the new MDL procedure that's in the U.S. that we're doing. It includes, replicates of spiked, LRBs, but then or spiked blanks, and then also replicates of blanks to determine the MDL. What approach did you use, given the fact that you have, some contamination? Is there a certain limit at which you say, we can't subtract that? I mean, if you have, what's the approach?
Well, basically for this, we use the blanks, and we use 7 blanks for statistical reason. And for our studies, because it was basically determining the baseline level, it was nothing to do with the legal action or any enforcement, we used 3 times signal to noise. But we can use 10 times signal to noise if you want to be more sure of the results. But when I showed you the results, it's all well above even 10 times signal to noise. Obviously, when you get into some of the effluents, if you go if you go 10 times signal to noise, it would be MDL, and then you put half the MDL. I rather put the number that I found rather than half the MDL at 3 times signal to noise.
Comment on the question that's been asked about the contamination from the container. Actually, I found the older the container, the better.
Yeah.
With time, because it's leaching all the phthalate, and nothing will stay there. So the contamination, the cross-contamination from the container will go down with the age of the container. It's much better to use like conditioned and it is old sampler than using a new one. That will help.
Just one comment, these samplers have been very well used.
Yeah, it's good. That's, yeah.
Okay. Any more questions? No? Please join me in thanking Dr. Ali one more time.
Thank you.
And Ali.